So now we're ready to actually use the confocal microscope to look at the tissue section that we have already looked at via epifluorescence. So first thing I need to do is plug in our confocal microscope computer so that the computer will now gain control over the microscope. The other thing I want to turn on is the lasers. These three are the power supplies for the lasers in the big black box here. So I'll turn on one laser, two lasers, and this third laser is the most energetic of both of them. It has a fan, or it would overheat. So I turn the power and the fan on. I don't know if you can hear that or if it'll be, but there's air coming out of the back of the lasers. And now I reach in here to use this key to turn the actual laser on. So now I have all three lasers and the fan turned on, so that we now have a new light supply. We no longer need the epifluorescence because we're already in focus on the microscope stage slide of what we want to see. So now that this is connected, let's open up the program again. And this time we'll ask it, please talk to the microscope. So it's thinking, oh hey look, it detected some objective lenses. It says, welcome to Fluoview FV1000, which is the name of the program that we opened. It says hardware initializing, and maybe you can hear it moving around some of the parts of the microscope to make sure that it has control of which mirrors are being used. Now I've already shown you this picture in a handout of the different controls that we have over the microscope by using this computer. So this one controls how the laser moves. This one controls how small of an area the laser scans over, so how zoomed in we are. And this one controls whether we're cutting the top of the basketball, the middle of the basketball, or the bottom of the basketball to see the optical sections. Of course, I can easily click on these to indicate which color I want to look at, or which laser I want to use, or even if I want to go back to epifluorescence. Up here are my buttons that control which light source is being used. So over here I've got the live view, and I'm going to move my live view onto the screen here so you can see what I am seeing. And what we can do is we can start with a focus 4x, which means the laser scans super fast, super dirty. Do not expect to see all the cells that you saw in the epifluorescence. We're getting a dirty cut through the cells. So we should only see little circles of the cells, not the full body of the cells. So focus 4x. Hey, look at that. It's showing me the blue color and the green color. And I can move around in the tissue section. Or if I want to see the whole tissue section at once, I can actually change my view here. So there's blue and green, it's showing me two at once. I'd actually like to turn on 3 lasers rather than just 2. So I'm going to stop the focus 4x, repeat stop, hitting this button right here. And let's see what the path of the lasers is. Let's see which lasers are on, which ones are we using, and how are they moving. So I've clicked this button to talk about where the light path goes. This is an image, a schematic, of what goes on from the outside lasers in this big black box through this tiny little fiber optic cable that comes around and goes in right here. These are the lasers. This is the epifluorescence. So we have to be very careful not to bend or break this, or the lasers can't come into this super expensive confocal apparatus. So here's our lasers on this computer screen. 405 is turned on. That's a deep blue, a purple. 488 is turned on. That's a blue light that will excite our green 488. Oh look, 543 isn't turned on. 543 is a good color to excite our red dye. So it's a greenish yellow, 543. So now we have 3 lasers coming out of the big laser scan unit. They bounce off of a mirror, they go through the fiber optic cable, they hit a dichroic mirror. We've talked about what a dichroic mirror does. And they are focused via other mirrors down onto our specimen. The laser being energetic, will cause our fluorescent molecule, like DAPI, or Alexa 488, or Alexa 594, to glow. And a longer wavelength light will come back through here. When that longer wavelength hits the dichroic mirror, it goes straight through it into the processing box. So this is what's happening back in here. We have all of these dichroic mirrors that allow the light, if it gets... Okay, so we want all three lasers to come in and excite our specimen, and the different colors of light to go to the different PMTs. They're called channels here because they'll show up on our image. So I can turn lasers off here, I can turn that channel off, or of course I want that on. So I've got all three lasers now are turned on, and their excitation, right, they will excite our specimen, and the fluorescent dye will give off an emission that will go to channel 1, channel 2, or channel 3, depending on which dichroic mirrors it passes through versus bouncing off. So I'm going to close the light paths and dyes, and now that I've got this third one turned on, because it wasn't turned on before, right? I've got it turned on, focus 4X, and now I got three colors. Tritsy is shown in yellow rather than in red because there is a Texas red, a darker red, but this is exactly the red that we want. So now we can see red, blue, and green. Oh no, there's too much blue here. Let's play with our gain and offset to change how much blue and green there is versus how much red. So I'm going to turn the voltage down on the blue laser. I call it blue laser, but of course it's a UV laser that's exciting our DAPI to make it glow blue. And I'll turn the green down a little. Of course I want to keep some of this interesting stuff there. Remember that the green expression was bigger than the blue expression. So I'm hopeful that I can see some of the surrounding tissue around these individual things that isn't showing up also in the blue. So I'll turn the blue down even more. And then any green that we see around the outside of that could be the real green signal that is throughout the cytoplasm and nucleus of these cells, just throughout. And then we better turn the red up, so I'm turning the laser light up, and we can see the actual outline of the cell. If I up the offset here, we can get rid of some of the extra red background. Let's do the same for the green. Nah, I think I want the green bright. Oh wow, that did way too much. So the gain is, as I'm just moving the scroll wheel up and down, if I was to click here, wow, that's too much green, right? Or click here, okay, I got rid of most of my green all at once. So notice the lasers are just scanning at focus 4X. So I want to get a good balance between the three colors before I take my actual image. So let's just see how this one works. I'm going to stop the focus 4X by hitting repeat stop. And now I'm going to go to XY scan. The laser will move much more slowly and should clean up this image a little bit, be able to get rid of some of the background. So this might take about 30 seconds to scan through the entire image. Here it's going through the green, and the blue, and the red. So let's look at what the lasers look like on the microscope. So look right down in here. There's the laser. It's not a big pillar of light. It's a super fine beam that is going blue, red, green, blue, red, green. Actually, it's more like UV blue, yellow, UV blue, yellow, UV blue, yellow. And each time it passes over one of these spots, it sends the information to the correct PMT. And so here you send the blue information, then the green, then the red, then you send the blue, then the green, then the red, then the blue, then the green, then the red. So the three images are all showing up at once. But the neat thing that we can do here is we can zoom in on any cell we want to, any region that has already been scanned. So here's the finished image, and now I'm zoomed in, or I can just immediately hit this button and zoom back out. So a single click of a button lets me zoom in and zoom out. That's enjoyable. Okay, the other thing I can do here is if I just double click on this image, I can select it as the one I want to look at right now. But what if I want to see all three colors in the same image? I want to overlay them. Then I'm going to right click and choose to show. I want to add a view. Well, I can just click over here. That isn't the way I wanted to make a fourth image to do this. As you can see, I've got a lot of turquoise where the green and blue are overlapping. I've got a lot of green where there isn't much blue. And I've got red on the outline there. But you know what? The red, when we saw it on the epifluorescence, was much brighter than this. So I'd like to see more red, and I think I better back off on the green. So I'm not going to save this image. Instead, we'll go back to our scanning, and let's go back to seeing the whole image. And I'm going to zoom in on just this one with all three colors at once. So now that I'm scanning with all three lasers at once, I can say, I want more red. And I can sure make there be more red. Look at now how you can see the outside of each individual cell. That's working really well, but unfortunately anywhere you see white means it's overexposed in the multicolor images. So I'll back off on red a little bit more. Now I don't want to lose that beautiful red cell right there. So I'm going to leave it like that for the red. And now it looks like we better back off on the green to not have quite so much overexposed pigments. The blue we had already backed off on quite a bit. If I add way more blue, right, look at how I can change the exposure of the different lasers. I have complete control over what each one is doing. So here in our tissue we can see the red, the green, and the blue. Wherever there was blue, there was also green, which is why we're not seeing blue separated. But we do see green in some areas that we don't see blue, and we do see a lot of red in areas where there aren't other cells. So now I'm going to be, because I have so much overexposure here, I'm going to be a little bit cautious, and I'm going to turn both the green and the red further down. And now I'm going to do something called a zoom. So what I'm going to do is I'm going to take this area and I'm going to optically zoom in by increasing our magnification here. So I can increase the magnification to double or triple, okay? And now I'm scanning a much smaller area with the same intensity of laser. So let's see what that looks like. So there's two ways to pick where you're going to zoom. You can either make this box smaller by increasing the zoom. I went from 1 to 2 to 3, and now I've got a much smaller box. Or, if I go back to the normal size, I can click this area and select what is it that I would like to focus on. So here's my focused area, okay, at about 4x magnification. I'll look at just these 5 cells that are in the plane of focus. Now there's a lot of cells underneath them that would also be glowing, but we don't get to see those in confocal until we make it three-dimensional. So let's go ahead and focus 4x at that smaller region. Look at the green versus the blue. And we'll repeat stop, and we'll do a higher intensity scan. So it's just as slow as the other time we took a picture. It's going through this area at a very slow pace with the laser to cover. We have optically zoomed in, and now we can get incredible detail of what's going on at that one cell. Looks like maybe I would like to bump up the red again if this cell doesn't come in here. Let's go back to multi-image. And you can see that there is some red, right? But because we're scanning in such a small area and not looking at anything above it or below it in the focal plane, we only see these 2 cells with a little bit of red around the outside of them. Okay, so I'm going to go ahead and stop that. So what else can we do besides zooming? Let's go back out. We can do Z series to make a stack. So what I'm going to do now is I'm going to hit this depth button, and instead of just taking one picture at one layer, let's take 135 pictures through the pollen grain. No, that would take too long. But maybe we can take 10 pictures and come back and show you what it looks like. So here I've got X, Y, and Z. Now the computer is going to control the stage moving up and down to control the focal plane. I'm not going to touch anything. I'm only working on the computer. So let's use this to figure out where we are in the tissue. So I'm scanning. Oh yeah, I got a lot of red, blue, and green right there. And now what I'm going to do is I'm going to click. Let's move up towards the top. So I'm moving the stage such that now I'm focusing on the very top of these cells. Oh, look, I'm losing all the staining. I've gone too far. Let's go back down some. Okay, so I'm in the tissue section here. This first tissue section will barely have any blue in it. I'm going to go ahead and set that as our start point. And now what I'm going to do is I'm going to, as we're still scanning, focus 4X, I'm going to move down, 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 down through the tissue section. Oh, look how bright that is. That's going to be so overexposed. Okay? And as I go down, 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 oh, we saw a lot of cool red cells there. I go further and further down in, and now I won't be able to see anything down here at the bottom, so I'll set that as my end, set end. So I'm going from 40 microns to 32 microns above its original start point when we started messing with it. So that means there's 12 microns of tissue. But didn't I cut the sections at 20 microns thick? I sure did. What happens is, on the cryostat, we take this piece of tissue and we attach it to the glass, and then we dry it, we bake it. What happens? The cells shrink. The other thing that happens is we wash antibodies over it. But antibodies have a hard time penetrating more than 10 microns thick. So the tissue might actually be there, but we don't see any staining because it's so deep down attached to the glass that when we washed antibodies over the top, they never penetrated all the way to the bottom. So we couldn't see it because there's nothing glowing. So here we have all three of our dyes have penetrated to a depth of 12 microns, and we'll now be able to take these images. And what we'll do is we'll step 1 micron, so this will be 1.09 microns, so we're going to go 9 slices, 9 pieces. I'll have to turn the focus 4X off, and now I want to do X, Y, Z. So I'm going to do depth, and I'll take each of the pictures one at a time. So I just press this XYZ, it goes to the very top, which we said was 40 microns up from the microscope slide. And it starts to scan it, and it's seeing some green, but remember how little blue there was at the very top, right? Because those cells, those got cut by the knife, and their nucleus fell out. There's no nucleus up there at the top, so it's not surprising that where our knife cut the tissue section, we're not going to see much blue. But as we go down to the next layer, and the next layer, and the next layer of these cells, we'll be able to see all the different colors. So let's go ahead and make this one large and overlay all the colors. I've got some blue. Where you see yellow, that's where the red, I've got some green. Where the green and the red overlap, you're going to get yellow. So I've got some fainter green here because there's some red there as well. And I've got some clear red down here, but I'm not seeing any of the blue yet. Okay, so this is going to take about 10 minutes, so we'll pause and come back, and then I will step you through each of these pictures that it took, just like I stepped you through the top of the pollen grain, the 135 pictures through the pollen grain, and we'll have 9 pictures. The second one is already more interesting than the first was. I'll show you those in a second. It is now scanning our 9th tissue section. So it's going through all the way to the bottom layer. This indicates that it's still scanning. Here it says we are 88% done, right? We're scanning section 9 of 9. Notice that the DAPI penetrated pretty far down. We got a lot of blue and no green right there, whereas the green dye antibody did not penetrate as far as the DAPI did. And so here you can see the laser scanning across our last section. And when it's done, it's going to pop up as a final image that will have those arrows at the top that I can move, just like I did through the pollen grain, from one to the next. So there we go, just finished the bottom corner, and it's done. It says, series done. Do I want to take 9 more pictures down into the microscope slide? No, I set my range of where the tissue was actually glowing, so I'm not going to hit append next, I'm going to hit series done. And here's that image, and notice the arrows, I can step through it. So let's make sure it's showing us all 3 colors. Okay, green is just overwhelming at the top. We don't see much blue, and there's only a little bit of red. Let's go step by step. There's section number 2, number 3. Wow, that's a lot of red. 4, look at all that blue as well. Section 5, section 6. Look at the red, look at the detail here. We have a nucleus on the inside with green into the cytoplasm and then red on the edge of the cell membrane of these cells. Next, number 7, number 8, and now we're getting down to the bottom of the slide where the antibodies couldn't penetrate. Oh, whoops, did I hit slide through at max speed? Let's slow that down. Here's your 9 tissue sections. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Next, what we can do when we stop the animation is we can turn this into a 3D image and see where do we see green, where do we see blue, where do we see red by clicking this 3D image here. So I'll make it 3D in Y. It says creating 3D animation. It is now counting where is there a green pixel. There's one, there's one, there's one, there's one in every one of the 9 images. And it does the same thing for the red pixels and the blue pixels. And it's creating this 3D image that it will then show us, and I will be able to rotate it on the side. So this image just popped up. Behind it, it's got our individual sections, section, 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 etc. From top to bottom. But now it's made a 3D animation. So this is like epifluorescence. You are now looking at all 9 pictures at once. They are all stacked on each other. So every bit of red, no matter where it is, you can see it. But what we're going to do is we're going to turn this towards you, okay? We're going to turn this on its side, and you can look and see which cells are more to the left and the right after we've turned it. So let's turn, 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 turn. Here is our 9 sections, optical sections, of this one piece of 20 micron thick section. Look, these cells are at the bottom. These cells are at the top. Do you remember we saw lots of green and very little red at the top? And now we're seeing blue at the bottom where we didn't, where the green never penetrated that deep. So we can see how many cell layers we have there. 1, 2, 3, 4, 5, maybe about 6 cell layers thick in our 20 micron section. So let's walk through that one more time. This is a fun optical illusion because it is a 2-dimensional screen and we're trying to look at a 3-dimensional object. So is it moving to the left or is it moving to the right for you? Is the left side moving backwards or forwards as you do this? Is it moving out of the plane towards you or back in? Let's speed it up. Pick a single cell, focus on that cell, and try to watch where it is, and are the cells near it, above it, or below it. Slow it down so you don't get too dizzy. Pick a cell. Is it a cell on the bottom or a cell on the top? Let's pick this blue one way over here. It's on the bottom cell layer. Let's pick this green one. Follow that cell. It's on the top layer. So here we've made 3-dimensional with only 9 pictures, right? That's only 1 micron per. It's not like the pollen grain where we took 135 pictures. That is completely possible, but our tissue is not that thick, right? And so we also used only a 40x lens. This microscope has 100x, and we didn't zoom at all. So we could have optically zoomed. And we could have looked inside a cell and taken a single cell and done a 3-dimensional image on it with 100 pictures through a single cell. So that's how to use the confocal microscope to take 3D images that you can tell what cells are on top and bottom, where's the blue, where's the green, where's the red, whereas you cannot tell that with epifluorescence. Epifluorescence is much quicker, but if you use all the settings here, we can clean up this image so that the background is virtually eliminated, and we can get a clean image for publication in a manuscript into a journal article using this, where we know exactly where each cell and each molecule in each cell is. So the last thing we're going to need to do is, of course, I'll want to save these cool images. So let's save and close this one. Instead of we're not Dr. Storer, so we'll go to Dev Bio, and how about I make a new folder here. This is Dev Bio 20, and open that up, and let's save this as our axolotl, right? So we type in what type of tissue it is, what it was stained with, okay? and what part of the body it was. We specifically have got some bone here, 3D animation, and I save that. It saves 117 images. Each little turn of the 3D images is saving. And so now we've saved that one and closed it. Let's also save our Z stack or Z series. So we have 9 pictures in a series, in a stack in the Z direction. So I hit close. I don't want to discard it. I want to save it. And so we'll call it the same thing. Okay. But this one is not. And I'm going to label here as well that we did this at 40x. There was no cleaning up, which is called Kalman averaging. There was no zooming, optical zooming. So this was the basic type of picture that you can take. Notice that our live image, we're not looking at anything right now because we don't have anything scanning. If I was just to hit scan one more time, there's our image where we are at the bottom. And if I just hit go to the middle, that's what the middle section looks like. So now I can go to the top, scan it, go to the middle, go to the bottom, now that I've set the regions. Okay, so let's stop playing with this. The most important thing when you are using the confocal is to make sure you turn everything off when you are done. If you walk out of this room and leave those lasers on, the lasers are over $20,000. They can burn out. So we need to make sure we shut everything down. So first thing I'm doing is I've already saved my images. I'll just close the program. Do I want to exit? Yes. Okay. I don't want to save this unmodified image, so I'll say no, don't save it. Notice that the computer is now losing control of the microscope. So you can hear that it is turning different things off. Here's our computer. Of course, we'll hit shut down. And we're done over here. But what about over here? Well, we've got lasers on, and lasers make a lot of heat. Oh, wow, that fan's blowing hot air now after using this for so long. Okay, so what I'm going to do first is I'm going to turn the hottest laser off with this key. I'm going to turn the next laser off, and our first laser off. So I turned the lasers off. What did I not turn off? The fan. This is the power for the fan. And the fan is still blowing to cool those lasers down. Now, looks like I have left the Excite Mini on, so I'll turn that off as well, because we don't need any additional fluorescence. But while we've got the universal control box on, we probably want to change the microscope so we can get our slide back out. Here's a handy little keypad, because I'm not attached to either of the computers right now. So I can hit 4X, and it changes it back to the 4X. So I don't have to use either computer. I've got a third computer right here that talks to the universal control box. And so now that it's at 4X, I can reach in and take my slide out, put my slide back with my others. What else do I still need to turn off? The power to the microscope. So I'll turn off the universal control box, because it's not attached to either computer. People always start with epifluorescence before they do confocal microscopy, so I'm going to hang this over here, and let's plug the other computer back in so it's ready for the next person to use. That's just, of course, a polite thing to do. And now we'll turn the power of the microscope off. So we're done with the microscope. Well, let's look over here at this other screen. What do we still need to do here? We've got this program open. We could save these cool images, right? Remember, this is epifluorescence, so we see all the cells, no matter what focal plane they're in. But I don't need to save these because I've saved these pictures before. So I will just close out of the program. Don't save any. Because it was not the last computer to be talking to the universal control box, it doesn't freak out saying, I don't have a microscope to talk to. And of course, we'll log out of this computer as well. Final step. The computers are shut down, the lasers are turned off, the microscope is turned off. Let's make sure we're not going to get dust in this thing. So we'll put the dust cover back on, and you have to be extremely gentle on this side, because if you were trying to flatten this out, you might actually with your hand hit the fiber optic cable and put a dent or a nick in it. So now the microscope is done, the computers are shut down. Why do I still hear a noise? I don't know if you can hear it in the camera or not. The fan is still on. Oh hey, that is so much cooler than it was just 5 minutes ago. And so now I'm going to go ahead and turn the fan off, put our slides away in a drawer where dust won't be falling on them. We often use this drawer right here as a central location for all our microscope slides. Extra racks for next time, and we're done for the day.